Look at these examples. If you actually want to run this example yourself, there's a little setup file for demo. O4 is the lesson name, and it's the first demo, demo 01, that requires to be running. I'm going to leave this running. I'm actually not going to actually demo this one in the full details. I'm going to use their provided information, but you can run this. You just need to connect with SQLT. And this is the password for it. They tell you that information in the notes at the bottom. And they tell you about this and the 3 script files that you could run. But if you did want it to run them, this was a prerequisite to do this particular little demo. It takes a few minutes for it to run, okay? And you could actually run this SQL file. We'll have a look at it, and I won't actually run it because we'll just use their output that they provide in this case. Some of them I use the output. Some of them I actually run, and sometimes I run them in different ways just for a variety. People get bored looking at one thing. So these are all documented with a little comment saying which demo it is, okay? Then what they're going to do is flush the buffer cache. In the past, we've had trouble before we introduced the flush the buffer cache command, and you need privileges on a database to do this, and we're going to give you full privileges on these test databases, so you get to try everything if you choose, okay? But in the past, if one statement load the data off a disk, and then the next run of this, another run of a similar statement we were testing, got to use it out of the buffer, the first one was more expensive to execute because it physically had to do the disk IOs. By flushing the cache, it makes both of them read the disk. It sort of levels a playing field. Unfortunately, they don't use it consistently within their examples. There's some places they should have added it a few more times, but oh well. That's neither there. This was the ability to put the trace name so it was easy to find so they could edit it later. So they just called it demo 01_01. And they're turning on SQL tracing. They execute the script file. They turn off tracing. Then they execute out of SQL Plus to get it terminated cleanly. And then they go and run tkprof against it. And when they ran the tkprof, this is a stripped down version of what they got. Okay, so I'll make this a little bigger so it's a little easier to read, so I can still get to the other things. Then it doesn't wrap out, it's still wrapped on me a little bit. One more time for making it bigger. There, it doesn't wrap. Okay, so this is the statement we executed, the one we were talking about that they showed you on the slides. And this is the information for what looks like one run. They parsed it once. They executed it once. They did the fetch 62 times. Depending on how many rows we need to return, we know returning one row is inefficient and a network connection. So we do a group of them, but quite often if you're returning a fair amount of data, it quite often takes a number of network fetches, passing the data from the database server to the client side through the network. This one actually took 62. The first two were neglectable, less than 1/100th for the parse and the execute in terms of CPU time. We did notice a little time during the parse, so it might have been a wait for something or the CPU was a little busier. No wait during the execute. And during the fetch, with CPU was immediately available. It took 7/100th to fetch the data, and it took that in the elapsed time, so it was readily available. I would suspect this is actually a little bit of wait time when accessing something during the parse phase. We had to do one disk I/O to read one block in memory as part of the cache. So there was probably some object wasn't in the library cache for the data dictionary, in the data dictionary cache. When we executed it, we did a lot of disk reads, and that's the maximum because we flushed the disk, the database buffer cache. So anything wasn't locked in memory because somebody was updated, it should have got flushed out. Okay, of those 1,456 reads off a disk, It allowed us to touch 2495 buffers in memory, and they were in query mode because this was a query. We were joining to and dumping the results. And it returned 911 rows. Okay, so not too many. It's not particularly really bad, but we looked at a number of blocks, more blocks compared to the number of rows. Perhaps there would be a better access path. And we have the information about the access path, or what a lot of people call the execution plan. Okay, and what we do is when we dump this out, we got the runtime statistics. And today in 12C, it gives you the first rows, the first time it ran it gives you an average, and it gives you the max. There was only one, so they all turned out to be the same. The number of rows we processed was 911 rows in this particular query. And then we have the execution plan. And execution plans get interesting read in them. And we're going to actually talk about a way of looking at them coming up in a chapter when we talk about interpreting. But just a little discussion with this. This one is doing a nested loop join, and it shows up as two nested loop statements. One is indented before the other, below the other. So the inner one is done first before the outer one. Okay. For the inner one, there are two legs to it. Logically, a left and a right-hand side of a binary operation. One is a full table scan of the customer's table. The next is a full table scan of the postal code table. And those both feed this nested loop. That produces a result table, which is the join of these two tables, that we treat as an intermediate result set. And we're going to join it to this thing, which isn't really a table. This double nested loop really depicts one of three ways that the optimizer can decide to execute a nested loop. And this was a little optimization to help with lookups in an index. If the data in the index and the data on disk don't follow each other reasonably closely, this is an attempt to minimize the number of IOs, the number of rereads we have to do. By batching up the access to the index for a bunch of rows that we're going to join by using a full table scan and an index scan of the postal. Instead of doing the join for each row as we get them one at a time, we batch a group of them up. That was done as an attempt to reduce the IO. There are actually three flavors when we get into the details of the join of a nested loop. Just this happens to be one of them. Okay. Now, what we could observe from this, is there a better way of doing it? It only used one index, the postal code primary key index on our second table. Is there a way we could possibly get it to use both indexes? Now, to do that, we'd have to change the table. As I mentioned, we want to make the way the data is stored in the two tables the same. So there's two logical ways we can do that. We can make the customer table have two columns for the postal code, just like the little postal code table does, the postal underscore codes table does. Or we can make the postal table look like the customer's, where it only has one column that represents the data. So they decided to do that, so we'll have a look at their first pass of doing that. So we'll open their input file. Okay. What they're doing in this case is they're creating a new copy of the postal codes table, just creating table as a select to get a new copy of it. Okay. Then we're going to alter the new copy of the postal that we happen to call the new copy of the customer's table. We're just copying the customer's table. Okay, and we added the two columns to it, the way it's stored on the postal code table. So we're making both of them have two columns to represent the postal code table. Then we need to update and put the data in those two new columns. So we have a little update that just goes through the customer to table and update them. It basically loads these two from the original customer postal code column. We didn't drop or anything. It's still out there. We're just using it to load it. Then we're creating an index on that 2-column postal code information so it looks like the other table. And then we're going to gather statistics. We've always said that having up-to-date statistics, this was a way of manually gathering it by calling dbms stats.gather table statistics. By the time you get to finish this course, this will all make perfect sense. You'll have seen these a few times. And then we name our trace file by just setting a name for it, turn on tracing, execute the statement, and there's a slight change to it. Because we restructured the data, we can get rid of the substrings on it. And what we wanted to do is to use the index on both sides. So the proof of the pudding is executing it, getting it in the trace file, and running tkprof on it. You could certainly do that themselves, but they provide the output. Once again, we made editing changes to it so it's less voluminous so we could just focus on the issue. So now we got our new query in here. It's just confirmed we're looking at the right trace file. We said make sure it's your query you're interested in. And the first thing we noticed, it took less time. The original output, it took 8/100, so there was a little saving in time. We cut it in half approximately. There was a little bit of saving in the elapsed time was even less. But even more important, we reduced by a little bit the number of blocks we need to touch in memory. Because we flushed everything, it had to reread it anyways. I don't worry about physical reads too much. If we tune down the logical reads, we'll have, if everything else is equal, pick the query with the least number of logical reads. It will tend to give you the better performance now. It may not look that way based on the time, but it will, okay? And it scales better as the data gets more voluminous, okay? So we saw a little change. Did it go much better? We cut it down by about 1,000 buffers we had to look at it. So how did they do it? Well, we did a nested loop. We did a hash join this time. And with hash joins, they chose not to use any indexes. So the rewrote caused a change in the execution plan that the optimizer chose. And it was a very slight improvement, but it didn't do what we were seeking to do. We were really trying to get it to use the indexes on both sides. So it did it less expensively because we reduced the number of blocks we had to look at to solve, to return I-900 rows, but not the way we thought. So is there a way we can get it to use the indexes? So we're going to try another strategy. We leave it structured like this, but let's do something else with it. So we have a third example for this one. Display it. The rest is just the same, but this time we gave it a hint. The hints are stored in comments. The /* is a comment in PLSQL SQL. It's actually a multi-line. It introduces the comment, and the comment ends with the //. We also have single line comments that start with a --. And you can use them, but then you couldn't put some of the statement. It just gets eaten as part of the statement. By closing it, we can put some other parts of the statement. And the hint occurs right after the first keyword: select, update, delete, merge, etc. Okay, and we need to put it in a comment. The goal is that if we give it to another database that is writing ANSI SQL standard and we wrote ANSI SQL, the other optimizer just thinks this is a comment, not a message for it. Ours looks for the 3 characters together, /*+. If they're not together, it doesn't treat it as a comment, as a hint. If I put a space between the /* and the plus, This truly makes a comment. And that's actually an interesting, fast way of disabling hints if you want to test it with and without the hint. Okay, you can disable. But if the space is there, the three characters are together, that's the message to the optimizer. Hey, optimizer, please do something a special way. Thank you very kindly. And as long as it can physically do it, it's really more of a command. It will try to do it today. It used to be at one time it took a lot to get it to do some of the hints. Now it's pretty good at obeying them. So this is a little message. I'd like you to do an index path. And here's some other secrets of Oracle you need to be aware of. If you use table aliases in your query, so we have the table name customer2, and then we have a short form for it, then you need to use the alias in the hint. If you don't, if I put employees2, but the alias exists, it ignores the hint, no errors, no warning, but I don't get the behavior that I'm expecting. And that's problematic, okay? So make sure we use the aliases. So we're telling it for customer2, we like to use the code 1 underscore code 2 index, that new index we created it in the previous lesson. This is a message, please do it using this index. Now that we told it to do it this way, let's see if it actually did. So once again, I just ignore the rest. Once you've seen a couple of them, you get used to them. And we'll just look at the output. So we'll display it. So here's our new query with our hint in it. So we're looking at the right statement. And now, okay, didn't change much in the CPU time. Okay, but now we've reduced the blocks even further. If we look at the second version of it, it's 1520. It's not a lot, but we reduced it further. And now when we have a look at the nested loops, it's still doing an optimization, but now it's actually using two indexes. It's using the index on the customer2, code 1, code 2 index, and it's actually using the index on the postal code. And we did see a reduction. If everything else is equal, if the elapsed time in CPU is pretty close to being equal, go with the lesser blocks we had to touch to solve the query. That's the better execution plan generally. So we were able to, it just took us a little bit to get there by testing. And the hints gives us interesting ways of testing it. It didn't really want to do this one without the hint. It wanted to do it the other way, but this one was slightly less blocks to look at, so it may in the long run be the better execution plan to go with. So now we're going to go back and have a look at the slide material for a bit. Some of these I do their way, some of them I do another way. So let's go back to the slides. We'll make it full screen so you can see it. We're going to be bouncing back and forth. So we had a look at this one. It's good to read the notes on the bottom of the page. This is another one looking at the index usage, okay, for a particular table. And when we might expect it to use the index and when we might not expect it to use the index. So we could have a look at these queries. We actually have a group of 5 queries. We numbered them A, B, C, D, E, F. And they do different queries against the original customers table, which was basically just a copy from the sales schema. We just made a copy of it, dropped some indexes, added the ones we wanted, and we're querying it. And usually for the customers table, the customer ID is the primary key. And the primary key has 2 conditions. It has to be unique and not null, because it's got to document every row. So each key we expect to return 1 row or 0 rows. We know the number of answers we're going to get. There's either 1 customer 1030 or there's none, because this is usually the primary key. So it's doing a unique lookup on the primary key, and what we want to know is, do we think it's going to use an index path or a full table scan. If an index path doesn't work, a full table scan always works to access a table. So we want to know whether it's going to do that or a full table scan. Okay. Now, they don't have any input data, but it's actually relatively easy to test this. And so we're going to look at testing a few of these, doing it manually. Okay. So I'm just going to go back to the environment over here. I'm going to shrink this out of my way. I guess I could actually close it up because eventually it's going to get kind of messy to look at them. And sometimes I put little things that make them think they changed them that I don't want to do. To test this, I can use SQL+. I've logged in with SQLT. If I want to confirm that, I can do show user. It will show me the account I logged into the database with. Okay. And we've got a little feature called AutoTrace. When we look at the different ways of collecting the execution plan, we're going to talk about this, but this is a very nice little feature. It was a new feature back in 7.3, I believe it is. We have a note on it later on, or 7.16 or something like that. So it's kind of useful to use, okay? And it has a bunch of setups you can use. If you type it wrong, okay, and make a mistake, I got to get the basic words, it's AutoTrace, but if I don't set anything, it will show me a little syntax diagram. So it shows me how to use it. It says I can either turn it fully on. If it's on, I can turn it off. Or I've got a couple other features. If I say trace only explain, and since this is an SQL+ command, it understands short forms. When you type select star from employees, you got to type the select fully, the star, and then from has to be fully. But this is SQL+ commands. They actually understand short names. So instead of putting trace only, I can just put trace. And instead of explain, I can just put an EXP as a form. Or I can ask for the statistics. And the one I like, we'll look at all these variations later on, but the one I like is set auto trace. And you can end it at the T if you want. Okay, trace only. And explain. And of course I could use the shortcuts, but that's the full form. If I get it all typed properly, what this will do is show me the execution plans without showing me the data. It actually executes the statement, but I don't have to wait for the data to scroll back. If it's a few rows it's going to return, it doesn't take long. But if it's going to return on 911 rows, it's going to take a while to scroll on my screen. That really does take a little time. I can save the time, but not looking at the output. It will also give you a little bit of statistics, but if I just want the execution plan, I can ignore that also. And then I can cut and paste this in. Let me grab the file a different way. That will make it a little easier. So you can look at these with Acrobat Reader. We also have Document Viewer that I'm hoping will let me cut and paste from this, or it's going to ruin my little demo. We'll see. This is real life, right? So we're just going to scroll down to the statement I was interested in. Takes a bit, make you dizzy. These were the ones. And now I can select it. Sorry about that. That works for me. Okay, now I can go to my SQL+ session. And I have a couple of them. So let's get that out of the way. This is the one I want. Now the other thing, the execution plans get long, so I do two things to make them easy to read. One is I make this big. And the second thing, the column, even though I made the terminal screen within SQL+, is still 80 characters. Let's make it bigger. So I can set line size 133 to acknowledge the old IBM printers. I've been around too long in the industry, right? Now I can dump in the statement I want to execute. And when it executes this, this is a statement I entered. It had the carriage return in it, so it went ahead and completed it with a semicolon carriage return. It says this is the execution plan. It gives me a hash value. We'll talk about where you can use that later on. Okay, and then it shows me how they're executing it. So it did an index lookup. A unique lookup on a primary key, we should use an index. Okay, so it did a index unique scan on a unique index for one value. If it finds a row ID, we use that row ID to pull up that row. If we don't, this becomes a null operator and we have no rows for this query. It won't have a row ID and we won't look up any data. And it gives us a little information. These are estimated statistics. It's estimating one row, worst case, 0 or 1, so it estimated 1 being positive estimate. This is either the estimate of a row length for a very generic table, or we collected statistics and we recollected statistics. So this is the number of bytes we expect to return for a row on average. It's not every row, it's the average row length for the customer's table, how many we expect. We also give you a relative cost factor. The lower the better, okay? And we give you the percentage of CPU during the step. It has to be some, it's less than 1%. So it averaged to look like zeros, but it's got to be something. Nothing is for free. And an estimate of how much CPU time this operation, they think it's going to take to do the index scan 1/100th of a second. Then we have to look up the data. They're estimating another 1/100th of a second for a total cost of approximately. It averaged to be just come out to be about 1/100th of a second to execute the statement. So it will give us a quick look at the execution plan. And it's kind of interesting as we're doing these to think about what you think it should be for a moment and then write it down and then see if it really is. It's all in the proof, right? So I'm going to get rid of this because I really want to use the other version of it. Okay, this version here that I can cut and paste from. So we'll put this one in the paste buffer. And we're going to execute this. The difference between this one, we wanted one, worst case, 1 out of n. Now the question becomes how many in here? Okay, and it turns out that I happen to know there's 55,500 because I keep working with this table every time I teach this class. You could do a count of star to take a look at see how many rows. Okay, this is looking for everything but 1. The 2 little square brackets represent not equals. It's another way of expressing not equal. It accepts this or the explanation point equals as a not equal. So if there are, my theory is true, there are 55,500 in here. What we're asking for is either all minus 1 or all minus 0. So either 55,500 or 55,499. That's a lot of rows. For that many rows, it won't use an index in reality. So you may have thought about it, whether it would use an index or not. Let's confirm that. So I got it in the paste buffer. All we have to do is execute it. Pull it down, and it executed, and sure enough, it did a full table scan. And it estimated what I was estimating. It said there's 55,500. If we find 1, there is 1 for 1030, that means we want 55,500 minus 1, or the answer they got there. It's going to do a full table scan because we want most of the rows. An index won't help us in that case. It will actually be slower to use an index. The number of rows we're expecting in this is the number of bytes, the number of rows times the estimated length of each row that we do the full table scan. This has a higher cost. The other one was 1 at the first step. This was 422. So it expects it to be more expensive, but it's based on what I asked it. It's got to use this execution plan to solve it. Okay, generally an index won't help this type of query. But we're estimating the IOs are going to be really quick. We can read all of that with only 1/100th of a second, and then we can process it, the whole statement, with 1/100th of a second. Okay, so we actually expect it to process quickly, even though we want a lot of rows. They're very optimistic in this one. So what is another example we have up here? Well, another one is we wanted to select customer first name, last name. We're getting the same information in each of them from the same table, but now we're looking at customer ID is less than 10. Now the question becomes, how many rows are customer ID less than 10? If there are lots of negative customer IDs, this could be a very big number and we could require a full table scan. If the customer IDs start at a numeric 1 or 0, then this can be a relatively small number, 9 or 10 out of 55,000. Then an index may help. It really depends on the data, and what I recommend is know the count for that predicate. You can go in and do this. So we're not going to do the query quite yet. Okay, I'm going to get this out of the way. Go find my original, oops, that was my original statement, was it? Yep. I'm going to turn off auto trace for a moment. Auto T off will work. And then I want to do select star, count a star. If I could type, I would be doing that, I guess. From, I already got the from in there if I remember. If not, I'll have to fix it. Okay, from customers where customer ID is equal. And sure enough, my theory was right. There's only 9 rows. 9 rows out of 55,000 is a very small percent. It's 1 or 2%. Maybe, I think it's actually less than 1%. So the index may be desirable in that case. Let's set auto trace on. Trace X, they said was the minimum. Whoops. And I can't spell auto trace, that would explain it. Sometimes I get the options wrong. Getting late, can't type today. Okay, execute the full statement, not my hacked up version to see how many are there. And let's see what it actually uses for the select statement. And this time it was estimating 5 rows. So we figured, we actually know there's 9 rows because that's what the count says. Okay, but it estimated 5, which is close. Estimate is an estimate. It's the same order, 9 versus 5, same order of magnitude. It's a reasonable estimate. It used a range scan on the customer's primary key to access the data instead of doing a full table scan. And this is cheaper than the full table scan. We have to do this as a full table scan. We were looking at, for the previous query, it was 422 units. This is 2 units. It's a little more expensive than the unique lookup because we had to do a range scan to get a group of rows, but it's not as expensive as doing a full table scan. Very cool. The last one is, last 2 are bigger ranges. Okay. We looked for customer IDs less than 10,000. 10,000 out of 55,000 is about 15 or 20%, something like that. We could calculate it, but I didn't bother. If that is true, I'm thinking full table scan. If it was a small number of rows, I'm thinking maybe a index path. So let's see, proof of the pudding is actually trying it. So back to our test, paste it in, we got everything set up. And this time, it executed it, but it fooled us. Tricky optimizer and those tricky engineers. Just goes to show you, you got to really work with the optimizer to understand what's going on. What it discovered by looking at this query, there is an index on customer ID, but there's only 2 other pieces of information we want from the table. Okay? The other 2 pieces of information are the customer name and the customer last name. What it discovered there are actually 3 indexes that will provide all the information for this query so it can avoid accessing the table. And it costs out different execution plan, and the lower cost one for a particular query wins. What they're doing is accessing the 3 of them. We're doing a fast full scan on 2 of them, the customer first name and the last name, and a range scan on the primary key. Okay. Taking the information from the 3 tables, logically join it together with 2 hash views. What the optimizer really knows how to do is join 2 things together at one time. So we do it as a double hash join, and it created a view that contains that data that we call an index join. It's a fictitious view it manufactured to process this. Because by doing that, it can get all the data for the query, accessing smaller structures. Indexes are generally much smaller structures than the tables are, and getting the data faster. So it fooled us, right? The last one is a range, but it's a relatively small range. Assuming they're just integers, there's only 9 or 10 in this range. Maybe it will do the index scan that we thought it would do here. Maybe it will find the index scan is cheap enough now to actually do it. So testing it is trying it. Proof of the pudding is actually doing it, as my mother used to say. So back to our SQL Plus session. Paste it in. And this time we did a range scan. It was estimating 4. I think it's a little higher than that, but that's okay. And it came up with the range scan, and it was down to being a cost of 2 again. Where the previous one, where we did it with this join, is midway between the full table scan and using the index in terms of cost. But it couldn't find the index, turned out to be more costly using it by itself. This turned out to be a cheaper way, so that's why it picks it. It always looks at different options that are available for a particular query based on your predicates and the data you want, and picks the lowest cost operation.